Okay, good morning. So last time we have concluded our lecture by introducing the notion of zero divisors. So let me briefly recall this definition. Last time. So today that will be definition 1. That let R be a ring and AB belong to R be non-zero elements, such that their product equal to 0, then we say that A and B are zero divisors. Zero divisors in R. So we have considered quite a number of examples of rings with zero divisors. But now let's have a closer look at the ring of integers modulo m, at the ring Zm. So our first theorem today would precisely describe the collection of all zero divisors in the ring Zm. So theorem 1. In the ring Zm, the divisors of 0 are precisely those elements which are not coprime with m. The divisors of 0 are precisely those elements which are not relatively prime with m. Prime with m. And the proof would go as follows. So the direct implication would be the following. So let's take n. Let's take n in Zm. And here we can just take any representative of the remainder class mod m. Really doesn't really matter. But let's assume that n is from 0 to m minus 1. Just let's take the canonical representative of that. And let denote D to be the greatest common divisor of m and n. So if D is greater than 1, if D is greater than 1, which precisely corresponds to the case m and n are not relatively prime, m and n are not relatively prime, then what do we have? So let's look at the following. Let's look at m divided by d multiplied by n. Okay, so because d is a divisor of m divided by d is an integer number, right? So this is this is an integer number, but at the same time, this is the same as m multiplied by n divided by d. And this guy is an integer number. So we have a multiple of m, which of course is equivalent to 0 mod m. Well, the opposite implication would be as follows.
Sorry, Professor, can you go back to what you were saying?
Yep, sure.
So what you're trying to prove in the first, on the first part?
Oh, I'm trying to prove that if we have an element which is not relatively prime with m, then it must be a zero divisor. Now, so let me.
So would you say if we have like a prime number, instead of m, we have a prime number, that means there's no divisors at all, zero divisor?
Excellent, and that will be precisely the one of the corollaries of this theorem.
Okay.
Actually, the first corollary. Thanks for introducing that. So that's great. Yeah, but here, just to repeat this once again. So suppose that we have n, which is not coprime with m, right? Then what we just proved is that n is a zero divisor in Zm, because we find something which, when multiplied by n, gives you 0 in the string. Okay, so but now we need the opposite implication, right? This is only 1/2 of the theorem. So the opposite implication would be the following. So now assume that we have now assume that we can find n1 and 2 such that their product n1 and 2 is a multiple of m. Okay, so if we know that the GCD of n and m equals to 1, then from here we must conclude, sorry, that's a typo. Let's say that the GCD of n1 and m equals to 1. So n1 is coprime with m. Then from here we must conclude that n2 must be a multiple of m, right? And 2 is a multiple of m. Well, if it's a multiple of m, then n2 is 0 mod m, right? So in other words, you cannot find, so let me rephrase that. In other words, you cannot find n1, which is coprime, with m, and at the same time is a zero divisor. At the same time is a zero divisor. Okay, so that concludes the proof of our theorem that all zero divisors in Zm are precisely the elements which are not coprime with m. Okay, and as you correctly remarked, there is an immediate corollary of this theorem. So let's say that this is corollary 1. Now that for prime p, for p prime, the ring ZP is actually has non-zero divisors. I wrote it badly. Let me say it this way. So ZP for prime P has no zero divisors. There's no zero divisors. In fact, later today we will prove that this is actually a field, but so far we know for sure that ZP for prime P is much closer to rings like Z or rational numbers or real numbers, where the product of two non-zero elements is definitely non-zero. Okay, so the existence of zero divisors, in fact, is closely related with the so-called cancellation laws. So, by the way, any questions so far about the theorem 1 or corollary? Okay, so let's move on to the cancellation laws. And let's first introduce the definition. So, definition 2. So let R be a ring. Now, we say that the right cancellation laws hold in R. Right cancellation laws cancellation law holds in R. Holds in R if if the following is true, that AB equals to AC equals to BC, AC equals to BC for non-zero C, implies that A equals to B. And this is cancellation, right cancellation law, denoted by CR. And similarly, we say that similarly, we say that left cancellation laws hold in R. Say that left cancellation law holds in R if the same story, C times A equals C times B for non-zero C, implies that A equals to B. That's the left cancellation law, CL. Now there is a beautiful theorem that, so it will be theorem 2 today, that cancellation laws hold in R if and only if R has no zero divisors. Cancellation laws hold in R if and only if R has no zero divisors. No zero divisors. Okay, so let's go ahead and prove this theorem. So let's start with the direct implication. Now suppose that cancellation laws hold in R, right? Suppose that CLCR holds, CL and CR hold. Okay, so what do we know? That then whenever A multiplied by B equals to 0, well, this is really the same as saying that A multiplied by B is the same as 0 multiplied by B, right? Which by the cancellation law would imply, and that would be the right cancellation law, that A equals 0. Okay, so there exists no AB in R which are not 0, such that AB equals to 0. In other words, there are no zero divisors in R. Okay, so that was short. So let's look at the opposite implication. Now, now suppose that there is no zero divisors. Suppose that there exists no zero divisors in R. Okay, so then consider the expression. Consider the expression AC equals to B times C. And let's assume that C is non-zero, right? Okay, so equivalently, we can add BC to the left-hand side and right-hand side. So this is the same as AC minus B times C, same as B times C minus B times C, right? Equals, well, which is of course equivalent to A minus B times C equals to 0. Well, because C equals to because C is non-zero by the right cancellation laws. By the right cancellation law, we can conclude that. Oh, sorry. We're proving the right cancellation. Sorry. Now, because there is no zero divisors in R, that would imply that A minus B equal to 0. And that's precisely this whole thing is exactly the right cancellation law. Let me scroll something. So CR holds. Okay, So any questions so far about the theorem or its proof? Now, as you might notice, in this proof, we proved only the right cancellation laws, but the story would be absolutely equivalent, that whenever there is no zero divisors, the left cancellation laws hold. And similarly for the first part, you can just use the left cancellation law to conclude that there is no zero divisors. So just as a summary, let me put this corollary here, which is again immediate from the theorem. Corollary 2. For rings, and that's very important here. I'll just make a remark about that shortly. Right cancellation laws hold if and only if left cancellation law holds. Cancellation law holds if and only if left cancellation laws hold. We say that this is a law. There's only one requirement, right? So it should be satisfied by all elements. Okay. Now there's an important remark. That you can note that the binary operation plus doesn't kind of enter the statement of corollary 2. So note that although binary operation plus is not explicitly used in the statement of corollary 2, and of corollary 2, it is crucial that R is a ring. It is crucial that R is a ring. And you can see that because we heavily used the addition in the proof. So of course the addition doesn't enter this CL and CR, only multiplication is there, right? But when we actually proved the theorem 2, we heavily used the fact that R is a ring. And in particular, this corollary 2 fails for associative operators when it's not a ring. Particularly the statement of corollary 2 wouldn't be true for general associative binary operation. Binary operation. Star from S cross S to S. And let me just give counterexample. Example 1. It's actually quite easy to construct. Let S be any set which has at least 2 elements. Which has at least 2 elements. Then define the following. Define the following binary operation from S cross S to itself as follows. So if we take X star Y, we will just output the left argument for all X, Y in S. Now you can check that star is associative. Now the point is, this is claim 1. Claim 2, that the right cancellation laws hold. CR holds. In other words, if you have X star Y equals to Z star Y, right? Just by the definition of this operation, this would imply that X must be equal to Z. And on the contrary, CL fails. CL fails. Because if you have X star Y equals to X star Z, this doesn't imply that Y equals Z in general. Because both of these guys, so this is X, right? By definition, and this is X. So what is really written here is satisfied automatically for all Y and Z. Okay, so this is an example.
Could you repeat that again, Professor?
Okay, so
why is it not true that the left cancellation laws hold?
Okay, so we just proved corollary 2 that for rings, the right cancellation law implies left cancellation law and vice versa. So the one holds is if and only if the other holds. Now the statement itself, the statement of the cancellation laws doesn't involve addition. So some might get an impression that this really would work for any associative binary operation. And what I'm saying in this remark is that this is not true. If we just have a general associative binary operation, not coming from multiplication in a ring, then the right cancellation law might hold while the left cancellation law might fail. So in other words, in the corollary 2, it is important that we talk about the rings. You cannot just say that you have multiplication on itself, which is associative operation. It is important that there's actually the addition and they satisfy all the axioms of the ring. And this you can see from the proof of the theorem. So any more questions?
Why does the left cancellation, why can Y be equal to Z in that?
It can, but we say that left cancellation law holds if this is true for all, right? X, Y, Z, where X is non-zero. So that's okay. Anyway, so that was just a side remark. Let's move on with the main part. Okay, so we talked a lot about the zero divisors. We kind of mentioned that rings with no zero divisors, for them we have better intuition, and that motivates the following definition of an integral domain. Integral domains. So that'll be definition 3 today. So we say that a non-zero commutative ring, non-zero commutative ring, commutative ring with unity. Commutative ring. Oh, let's say this is ring D with unity 1, which belongs to D, is an integral domain if it has no zero divisors. Is an integral domain if it has no zero divisors. Okay, so we need this definition because one can prove a lot of nice things about integral domains. And in particular, okay, so let's just do a first kind of relatively easy theorem. Theorem that every field is an integral domain.
Professor?
Yes?
Oh, I was asking, what does unity 1 mean?
Oh, so we say that that 1 belongs D is a unity if 1 multiplied by x equals to x multiplied by 1 equals to x for all x in D. So that's what we meant by unity. So we kind of introduced this definition last time. Okay, so now every field is an integral domain. Every field is an integral domain. Okay, so the proof would go essentially in one line. So we know that by the definition, field is commutative, right? Commutative ring with unity. So the only thing we need to prove that it has no zero divisors. So let's take any element in our field minus 0, any non-zero element. Well, from here it follows there exists an A inverse, right? There exists a multiplicative inverse of this element. Well, from here we can conclude that AB is not 0 for every non-zero B, because if it is, we kind of multiply both sides by A inverse, right? And we will get that B is equal to 0. Okay, so then this means that there are no zero divisors, and hence that every field is an integral domain. Now, this is not very interesting, as you might guess, right? So of course, kind of we explicitly required every element to have multiplicative inverses, right? This is a very strong condition for a ring to be a field. But what is actually even more surprising is that every finite integral domain is a field. Every finite integral domain is a field. Okay. And the proof of that is based on the following. So if we take an element, so that A belongs to G minus 0, then what we can look at, we can consider all the multiplicative powers of A. Consider A to the J, consider A to the J for natural numbers J. Now we know that there exists only finitely many elements in D. We know that there is only finitely many elements that there's only finitely many elements in D. Well, from here it follows that sooner or later the powers of an element A should coincide. So there exists J1, J2, which are not equal to each other, such that A to the J1 equals A to the J2. Okay, so without loss of generality, let's assume that J1 is what do we know? Let's say J1 is less than J2. Otherwise, just rename them. Okay, so let's assume that J1 less than J2. So then what do we have? We have that A to the J1 equals to A to the J1 multiplied by A to J2 minus J1, right? So by the left cancellation laws, which holds because there is no zero divisors. Note that by theorem 2 CL holds in D. We can conclude that 1 equals to the A to the J2 minus J1. Well, so in other words, there is a finite power of A, which is the unity element. Well, from here you can immediately construct inverse, a inverse, precisely as you would do the inverse in a finite cyclic group, right? You would take A to the J2 minus J1 and just subtract 1. And that belongs to D minus 0. So every non-zero element is invertible. 0 element is invertible. Now this is a really neat trick, right? Because there's only finitely many powers which can be distinct, and sure enough, A raised to some power is 1, and this allows you to get a formula for the inverse for the multiplicative inverse of A. Yes.
How do we know that the powers of A can't be 0?
Great question. Sorry, I kind of swiped this under the rug, and they can be 0 because there is no 0 divisors. So that's an excellent point. So note that a to the j not equal to 0 for j greater than, well, greater or equal than for all j in n. All j in n. Because assume it does. Did proof this by contradiction. Suppose a to the j, j is the smallest number, j is the smallest number such that a to the j equals 0. Note that a is not equal to 0, so j cannot be equal to 1. Then consider b to be equal to a to the j minus 1. It is non-zero because j is the smallest number such that a to equal to the 0, a to the j equals to 0, right? And then a b equals to 0 for a non-zero and b non-zero. But this is impossible. This is impossible since d has no 0 divisors. Okay, thanks. That's does it clarify the question? Thanks. That's important thing to mention here, that all a to the j are non-zero. And let's just circle this whole thing. And this goes to here. Okay. So any more questions about the theorem or the proof? Now we were proving this theorem precisely because we want the following corollary. So we already proved that ZP for prime P has no 0 divisors, right? So now we will get, and this will be corollary 3. That ZP is a field for prime P. ZP is a field for prime P. In other words, now we can say that all non-zero elements of ZP have multiplicative inverses. all A belongs to ZP minus 0 have multiplicative inverses. A inverse in ZP minus 0. Well, now corollary 4. Corollary 4 would be that the set ZP cross is the set of elements which having multiplicative inverses is precisely ZP minus 0. Okay. And this is kind of brings us to the following theorem, which is the essential part of the so-called Fermat theorem. So let's call it theorem. What was the previous one? The previous one was theorem 4, so that'll be theorem 5. Theorem 5, which is formulated as follows. So let A be an integer and P be a prime number not dividing A. P be a prime not dividing A. Then what we know is that A raised to the power P minus 1 is 1 modulo P. Okay, so how do we prove this theorem? So proof. Consider image of A in the ring Zn, right? Then what do we have? We have that A belongs to Zn minus 0, which is, Zp minus 0, which is precisely the set of all invertible elements. Now, by theorem 1 from last time, theorem 1 from last time, Zp cross with the binary operation multiplication forms a group. Now, the order of Zp cross, right, is P minus 1. Because the order of every element, order of A in ZP cross must divide the order of a finite group. The order of a group we get that A to the power P minus 1 equals to 1 in ZP cross. Let's say, to avoid kind of confusion between the integer number A and its image in ZP, let's denote the image by A overline. And this is essentially equivalent to the A to the P minus 1, P equivalent 1 mod P. Here we go. Okay. Now, corollary of this theorem 5. Corollary 5. And that's Fermat little theorem. Is that for all now, for all integer A, and prime P, for all integer A and P prime, we have that A to the P equals to A mod P. Well, proof is essentially two cases. Case 1, A, well, P doesn't divide A. P doesn't divide A, follows by theorem 5, follows by theorem 5. You just multiply both sides by A. And case 2, P divides A is immediate because in this case A to the P equals to A equals to 0 mod P. No, both of them are. Let's do it this way. Equals P equals to 0 equals to A mod P. Here we go. Now there is a neat generalization of this method, and there is so-called Euler's theorem. So before, by the way, any questions so far? Okay, so what we just did, we described kind of completely the case when the case of ZP when P is prime. So we proved that there is no zero divisors, that every single element has a multiplicative inverse, and that kind of this collection of non-zero elements, they form a group. They form a group with respect to the binary operation multiplication coming from the ring. But now what really happens when your ring have zero divisors? So now Now, what about the case Zn? The case of Zn when n is not prime. It turns out that this is a question. It turns out that we can still describe the set of all invertible elements. We can still describe the set of all invertible elements and even prove the generalization of corollary 5. And even prove generalization of Fermat little theorem, known as Euler's theorem. So let's get started with this part. But by the way, before any questions about the case of ZP, of the ring ZP for prime P? Okay, so what we already know in the case of Zn, is that what is the subset of zero divisors, right? So one of the theorems we proved earlier today, it tells us that elements of Zn are zero divisors if and only if they are not coprime with n. However, this doesn't immediately imply that, you know, kind of the elements which are not zero divisors have multiplicative inverse. But this is in fact true, and that will be our next theorem. That'll be theorem 6. Okay, so the set Gn, which is a subset of Zn of elements of Zn which are not divisors of 0, which are not divisors of 0, consists precisely, well, forms a group let's phrase it this way: coincides with the group of precisely with units. So in other words, all elements in Zn which are not zero divisors, there's must be units. And here how the proof will go. So we will basically use the same trick as we employed in the Theorem 4. So we will look at the different powers of an elements in Z and cross. Of an elements in Gn. And we will kind of observe that every element there must have a multiplicative inverse. Okay, so on the first step, we need to show that the set Gn is closed under multiplication. Step 1, we will show that Gn is closed under multiplication. Now, for this part, let's take A and B in Gn. And our goal is to prove that their product is not a zero divisor. In Gn, let A, B belongs to Gn. We need to show that AB belongs to Gn, namely that AB is not a zero divisor. Well, assume the opposite. And say ABC, say ABC equals to 0 for C not equal to 0. Well, but then A times BC equals to 0, right? So then A times BC equals to 0, and BC is not equal to 0 because B is not a zero divisor. This would imply that A is a zero divisor, that A is a zero divisor. So here we get the contradiction with our initial assumption. Get the contradiction with our initial assumption that AB belongs to Gn, while AB, their product, doesn't belong to Gn. Okay. So the set of elements which are not zero divisors is closed under multiplication. And note that here we use nothing specific about Zn, right? It really it will really work for any commutative ring, right? So that the set of elements which are not zero divisors is obviously closed under multiplication. Okay. Now on the step 2, we will prove that every element which is not zero divisor is invertible. We will show that every element in Gn has multiplicative inverse. Has inverse. Okay, so let's take A, which belongs to Gn, and as in the theorem 4, and consider A to the J for J being a natural number. Similarly to theorem 4. So by step 1, we know that AJ belongs to Gn for all powers of this element A. But again, there's only finitely many. But there is only finitely many elements in Gn. So there exists J1, J2, two different natural numbers, J1, J2, two different natural numbers, such that the powers of A are the same. Again, without loss of generality, let's assume that J1 is less than J2. So what do we have here is that we have that A to the J1 equals A to the J1 multiplied by A to the J2 minus J1. Let's bring everything on the left-hand side, right? And factor out A to the J1. So what we get is that A to the J1 is 1 minus A to the J2 minus J1. And that's equals to 0. So that's by the R3. Well, R1 plus R3. 1 plus R3. Okay, so now here's the trick. Let's call this thing B. And because A to the J1 belongs to Gn, in other words, A to the J1 is not a zero divisor, the only way this can happen is if A to the J2 minus J1 equals to 0. Okay, this would mean that a to the j2 minus j1 equals to 1. Well, but then we can take a inverse to be a to the j2 minus j1 minus 1. And that belongs to our Gn, obviously. So every element in Gn has multiplicative inverse. Now, hence, Gn is a subset of Zn cross. Well, because the other inclusion is immediate, because the inclusion Zn cross subset Gn is essentially by definition holds by construction, holds by construction, we conclude that these two sets actually coincide. I used small n's before. Sorry about that. That's what happens when you start rushing towards the main statement. This is n small everywhere. Gn coincide with Zn cross. And that concludes the proof of our theorem. So any questions so far? Now, here's an important thing to make, an important remark to make, right? Step one is not specific for our case. It's always true that all elements which are not zero divisor, the set of elements which are not zero divisors is closed under multiplication. But this by itself doesn't imply that they are invertible, right? And that's precisely what we did on the step 2, and which is very specific to the case of to the case when this set Gn is finite. Remember, this trick will never work when Gn is infinite. Okay, so now we have the description. Now we have the description of all elements in Z and cross. Now let's just put this corollary. Z and cross consists precisely of those elements which are coprime, are relatively prime, with n. Okay, and actually the number of elements in this Zn cross has a name. It's the so-called Euler phi function. So that will be our definition. Oh, I have forgotten what will be the number of this definition, probably definition 3. So define function from natural numbers to natural numbers as follows. So phi of n So phi of n would be the order of a group Zn cross when n is greater than 1, and just by hand we will say that phi of 1 equals to 1. So this phi counts the number of elements in Zn which are not zero divisors. And kind of remark for prime p, we have that phi of p equals to p minus 1, right? Because every element in ZP which is not zero divisor. Okay, and now we're basically ready to prove the theorem that will be probably theorem 7. Theorem 7. And that's Euler's theorem. Euler theorem. So let A be an integer number, and A is relatively, and suppose that A is relatively prime to n, which is a natural number, minus 1 to n greater than 1, then what we have is that A, when raised to the phi of n, has remainder 1 modulo n. Okay, and with all the theory we've built up, the proof would be essentially one line. So let A bar in Zn be a natural image of A in Z. In other words, A bar is nothing but A plus NZ, the coset. Then if A is relatively prime, to n, we have that this A bar belongs to the multiplicative group of the ring Zn cross. And the order of this multiplicative group is nothing but the Euler phi function, because the order of A divides the order of the n cross, we conclude that a bar raised to the power phi of n equals to 1 in the n cross. Or equivalently, a raised to the power phi of n has a remainder 1 modulo n. Okay. So this is a great place to stop. So now I'll be glad to answer your questions.
Do you know how to classify the group Gn if all the numbers relatively prime to n?
Oh, that's a great question. In fact, that's kind of it's algorithmic, but it's not straightforward. There is no that's why we need kind of, even for the order of this group, we need special function which is called Euler function. So it's kind of there is no simple formula which gives you the answer, but it's possible to examine that, and that's there will be a bunch of actually homework exercises to compute these groups. So it has a lot, as you might guess, it has a lot with identifying elements which are not coprime with n, right? To look at the possible divisors of n, etc. So that's a great question, but it doesn't have like one sentence answer. So that's. Any more questions?
Thank you, Professor.
No, thank you. Okay, so then I'll just restart the session and continue with the FSRs. So.